Okay. So if you guys, yeah. Okay. Wait, so welcome. Today we're going to hear from the grad student in my group, Sumitra. He is in his 4th year, and he's been working on the optical experiment in our lab. He's been the senior grad student now for about a year. He's worked on a lot of projects within that. In first paper was cooling lithium. So for people who don't know, we're a lithium cesium molecule lab, but we've been really focused on atoms to cooling techniques. So he has a great paper on first cooling of lithium in a tweezer. And then we did a little theory project, which turned into a very, very big theory project. So he's kind of been a theorist in that paper now, but he's actually not going to talk about any of that. He's going to be really focused on the last year, what we've been doing, and looking at this new transition that not a lot of people have.
Thank you, John. So yeah, like you said, I'm a 4th year physics PhD student. Even though I'm never in physics, I'm always in chemistry. Thanks for having the lab in chemistry. But yeah, today I'm going to talk about cooling and imaging a single cesium atom using quadrupole transition, which is the transition is new. Like using this transition for imaging and cooling is new in atoms. Never for atoms, to my knowledge, any quadrupole transition has been used to image or cool a neutral atom. So I'm going to talk about that. This image is actually pretty special to me because you can see 1 million cesium atoms at the center. Now it's very, like, people know about it, and this is a magnet optical trap. So this is our glass cell in which we trap cesium atoms. I started my journey in this lab looking at this image. So this is actually, they already had a cesium atom trapped in a tweezer when I joined. So only, I guess you can say that only the line that we are using to image and cool has changed, but we have come a long way, and I think I will prove that through this presentation. So let me tell you a little bit about our lab. There are 2 groups in our lab. One is ultra cold group and one is quantum optics. I'm from ultra cold group, so today I'll just discuss that part. Like he said, we have dual species in the lab. We have lithium single atom and we have cesium single atom. These are images for magnet optical traps for both. One is cesium on your left and one is lithium. Then we go from magnet optical traps, which is ball of atoms, to a single atom of lithium and cesium. This is the image for a single atom trapped in tweezer. And then the new thing that we are doing now is using a new line for cooling and imaging in cesium, which is a quadrupole transition. I will talk about all the energy levels and everything that is going on this line. But let me first motivate why this line is interesting. So let me start with why 6s to 5d transition in cesium is interesting at all. So there can be 2 motivations for it. One is actually we can use it as a clock transition. People actually, I started motivating this because we actually are not going to do a clock transition in our lab, but there is a research group in physics department itself. I think Chen Lug's group is interested in this transition as well, and then even in Wisconsin, Madison, there is a group who is trying this transition for a clock transition. So just to give you an overall picture, I will also explain as this transition's application as a clock transition. Then what we are going to use it in the lab is as an imaging and cooling beam. So I will also explain that. So let's first start with motivating why this transition is useful as a clock transition. So we have come a long way actually to doing atomic clocks, starting with, like, of course, initially we used to take as a reference, we used to take celestial bodies and the periodic motion of the celestial bodies to reference our clocks. But then from there, from mechanical oscillators, we have now come to electronic oscillators, and then there has been a lot of change. And now we use atoms as a reference. So, but then if you see, the ingredients for a good clock are actually still the same. So what are the ingredients? The first one is we of course need a local oscillator that will produce oscillations that will be referenced with those are the ticks that we will measure, and we will say that this is a clock. So this is in the image, you can see a quartz oscillator. That's like the basic oscillator you can get, and then that is still used, by the way, in all the clocks. So it is just a piezoelectric. So you just send the electrical pulse and then it oscillates, and you measure that frequency. That frequency is like tens of kilohertz. So from there you can go to electronic oscillators, which is then it is a frequency counter. this frequency counter is, the upper limit is like tens of gigahertz. So electronically speaking, tens of gigahertz is the limit to which you can count pulses. And that limit comes into the picture because later, anyway, even if we use atoms, we are going to need electronics to count pulses. So that's why the frequency counter is needed. And then you use a reference transition to lock, because if you have multiple clocks and then all the clocks should agree with each other, right? So then that's why you use atoms, because atoms are identical in any part of the world. And then if you use a transition in the atom, then if you lock to that transition and you do reference to that transition gives you a good reference point, and that's why your clock will be very stable. So which transition do you use in an atom? Because there are multiple transitions that you can do. So for example, going from a ground state to an excited state gives an optical transition. If you are coupling between the two ground states, that's a hyperfine transition, or you can do a fine structure transition as well. So now which transition you choose decides what clock it is, because all these are atomic clocks, but then the transition that you use, if it's an optical transition, then it is called as optical atomic clock. If it's a microwave transition, like the hyperfine structure of F3 and F4, then it is called as microwave atomic clock. And this microwave atomic clock is the current standard actually, which is used to define a second. So let's look at that clock. So we need a high frequency reference transition for a clock so that we get more ticks and we count it and it's more accurate and less uncertain. So now for atomic clocks, these are the two current ones that are most popular. The one on your left is actually the Cesium microwave atomic clock. The reason why this is like vertically so huge, it's like they do this crazy thing where they have trapped atoms and they just throw it up in the air and then they pass it through the microwave cavity twice. And that's how they reference it to the transition that we were looking at earlier, which is a microwave transition. So the tick rate here is basically tens of gigahertz. Mainly, you can read up about this, but the aspect that I want you to focus on here is the size and the scale of this atomic clock. So you can imagine that you will never be able to, at least in the near future, you'll never be able to commercialize it and make it like very compact for any clock that you want to make miniaturized, for example. So this takes a lot of space. And then this is, even though this is the current unit which defines a second, but this is not the most precise atomic clock that is there around right now. The most precise one is based on strontium, and that uses an optical transition. So there is a trick that was relatively recently discovered, that you can convert your optical transitions accuracy to, because like I said, counting electronics is still tens of gigahertz. So if you have hundreds of terahertz transition and then you want to maintain that accuracy, then there is a trick with frequency combs that these guys do. But you can read up about it in this review. But the thing that I want you to focus on is, for making this optical atomic clock, which is, by the way, 4 orders of magnitude better compared to the microwave clock on your left. Using this atomic clock requires a lot of lasers. So a lot of different wavelengths that are also not commercially easily available. So they have to make those wavelengths. And then, of course, the size is also a matter. But then strontium, on the other hand, compared to cesium, is again not very simple to produce and trap. So it needs a Zeeman slower. So that increases the size of the apparatus, because you can see a long arm here. That's like the Zeeman slower arm. So for optical atomic clock as well, you require multiple wavelengths, and then you require the Zeeman slower, which increases the size of the apparatus. So now where I'm going with this is, if you just, okay, we need a parameter though to compare these two clocks. So what is the parameter? The parameter that they quote in their papers is Allen deviation, which is basically, you can imagine if you are using a line for a transition. So then narrow the line width of that transition divided by the frequency gives you fractional uncertainty. But just by quoting fractional uncertainty, you cannot compare two different clocks, because in the measurement process, we also know that the amount of time you spend in measuring something gives you more accurate results. So that's why it has to be normalized with respect to time. And that's why this parameter gives you a measurement for that, which is a measure. Allen deviation is a measure of overall fractional frequency noise as a function of measurement time. So if you compare the two best clocks in the world right now, then they are different by 4 orders of magnitude. So strontium lattice clock is actually 4 orders of magnitude better in uncertainty compared to the SI unit of second, like which defines SI unit of second right now. But the interesting part is, so then both of these require like large apparatus and also some like some wavelengths that are not easily commercializable. So there is a space, there is a little space, white space that you can see in here that is available for a alternative, which can be this transition that we are looking at in this presentation, which is cesium at optical atomic clock. So there is a proposal by Mark Safman in University of Wisconsin that you can use a transition in cesium to get this optical atomic clock working. And the idea there is you have this transition where there is 6s1, the ground state is 6s1/2, and then you send your electron to 5d 5/2. It has a branching ratio to 6p 3/2 and again back to 6s1/2. But you can see looking at the branching ratio, this transition predominantly decays via 6p 3/2 and comes back down to 6s1/2, emitting 852 nanometer photon. So you can see multiple things here. This first is a quadrupole transition. So 6s1/2 to 5d 5/2. So L equal to 0 to L equal to 2. So there is a 2 angular momentum change here. And while coming back down, the emission happens via 2 dipole emissions. So the excitation happens via like a quadrupole line, and the emission is a combination of 2 dipole processes.
Or you just look on screen again.
Here. Yeah. So you start with the ground state, and then once you excite the atom, then it goes to 5d 5/2 state, and then it decays via 6p 3/2 and comes back down to the ground state. So if you use this transition, and then if you have a cesium, if you have cold cesium atom wrapped in the lattice, then what you can do is do feedback on this transition where it will emit 852 nanometer photon. So you excite with 685, and then you get back 852 nanometer photon from this transition. And then if you form a clock using this feedback mechanism to lock to this transition, then what you get is it's a much simpler system compared to the other 2 systems that we looked at, which were used for atomic clocks. So if you make a clock out of this is not a clock talk, but then still this transition is, since it has the potential of making a clock, that's why I'm emphasizing on it. So, and the group in Wisconsin Medicine is actually trying out this clock. And if this clock works, and if it gets the uncertainty that is quoted in the paper, then it can be a good candidate to miniaturize this clock. Because now if we know the other 2 clocks, we got a number to compare other 2 clocks. So where does this cesium clock stand compared to the other 2? So it's not doing as bad, because it's better than the current one that is used for defining a second. It's not as good as the best clock in the world, but it's 2 orders of magnitude better than the current one. And the selling point here is like you just need 3 different wavelengths for it. And all these 3 wavelengths that you see here, 852 nanometer, 803 nanometer, and 685, all these 3 are easily available wavelengths compared to the ones that are needed for strontium. And also it doesn't require a Zeeman slower or an oven. So cesium is much easier to trap. And then people have been trapping cesium atom for like 2 decades now. So it's very well known. And so that's why it basically being a compact apparatus and then still being 2 orders of magnitude better than the current one gives this a selling point that this transition can be used as a clock transition. But moving on, this is just one use of that transition. That's why it's an exciting transition. But the way we are going to use it is for a imaging or a cooling beam. So let me motivate why is it useful for imaging and cooling for us, since it's a narrow line transition and it is also a quadrupole transition. So again, like we looked at what are the ingredients for having a good clock. Let's see now for imaging beam or cooling beam, what is necessary for us. One is we want a narrow line width. I have a great slide later to explain why we need a narrow line width, but for now, having a laser's line width very narrow helps us drive specific transitions in the atom, in the discrete motional states of the atom. So I will explain that. So we want a narrow line width, and we also want a cycling transition where if you put the atom in, let's say F is equal to 4 state in the ground state, and then you're sending the atom to F is equal to 6. You do want the atom to come back to F4, because if you keep a laser line on and on resonant with 4 to 6, then it helps if you are doing imaging or cooling. Both works with scattering number of photons. So with scattering the number of photons, you do want to cycle from 4 to 6 continuously. And it won't help if it decays down to some other state and then you lose that cycling transition. So that's why the cycling transition is also important for us to do imaging and cooling. And we also need a narrow line width. So if these two are the ingredients for good cooling, then how does this transition help us? So firstly, doing cooling and imaging with quadrupole lines is not new entirely. It's done a lot of times in ions, and they are doing it for a longer time. But the reason is because they have this readily available narrow lines. Because if you see their level structure, then this is strontium 88 level structure. And you can see the lowest lying states are D states and not P states. So they are actually able to use these transitions, which are extremely narrow lines. So this is like 400 millihertz narrow line. And they readily have this transition available. So they have been using it for a long time. But in alkali atoms, in like neutral atoms, we generally use D2 transitions. We generally use dipole transitions that are 5 megahertz wide. So you can see there is like orders of magnitude difference between the line width that is used for ions, quadrupole lines, and alkali atoms. So if we can find a narrow line transition in alkali atoms is also, the motivation to use alkali atoms is also, it has the simplest structure because it has one electron in the valence orbit. And that's why they are the simplest one to understand, but you don't get narrow lines in them. So if you can get best of the both worlds, that's why people were searching for narrow lines in alkali atoms, and we found one. So currently, no one is using a narrow line for alkali atoms at all. So we want a cycling narrow transition for good cooling. So with that motivation, with that motivation, we start using a quadrupole line. But why is quadrupole interesting at all? I mean, of course, it's not a dipole, that's why it's interesting. But for quadrupole, we can actually do quadrupole transitions using two different methods. So this is something that I emphasized when I started this project actually. That you can use two photons to transfer one angular momentum each to the atom to get the two angular momenta. Or you can use one photon and use two different angular momenta that is present in the same photon to transfer to the atom. So that's what was emphasized when I started this project. So the photon actually has two angular momenta. One of them is a spin angular momentum, which we are very familiar with. So the usual Hamiltonian that we always look at is the E dot E Hamiltonian, where the dipole moment actually couples with the polarization of the electric field. So when they couple, then the spin angular moment of the photon is what we transfer to the atom. So it's actually the electric field that is doing circles for sigma plus versus sigma minus. So this is the electric field that is going around like this. And then that's the electric field, that's the angular momentum that you transfer to the atom. But this is intrinsic angular momentum of the photon. But now you get also extrinsic angular momentum of the photon, that is orbital angular momentum, where the photon itself is doing this. And then if you're able to transfer that angular momentum as well to the atom, then what you can do is, using single photon, like I said, you can transfer two angular momenta, which is pretty cool. And the Hamiltonian that we look at for that is, if you do multiple expansion, then the quadrupole moment actually now couples with not the electric field, but the gradient of the electric field. So what drives the quadrupole transition is actually the gradient of the electric field and not the electric field. So you can imagine that now in our case, when we have any beam shining at the atom, then we are looking for gradient of the electric field to drive transitions and not the intensity of the electric field, intensity of the beam, which is in itself pretty cool. So you can see that these are now the two different angular momenta that we want to transfer to the atom, and then do this quadrupole transition from 6s to 5d. So this is the transition that we are driving always in the lab these days. So before explaining how the cooling works and before showing you the results, let me talk a little bit more about our system. So we have single atoms trapped in the tweezer, and then tweezer is of course a rate detuned trap, where at the highest intensity we have a single atom trap. And then when we are talking about cooling in a single atom system, so then the cooling actually, whenever I talk about cooling to people who are not so familiar with laser cooling, let's say, then they always imagine something in free space where the atoms are going around in the space. So once you have trapped a single atom in the tweezer, the cooling is not just making the atom stop at a certain place, but it is also reducing the motional level. So how we imagine when we think about atom in a tweezer, how we imagine the atom is not like this. This is how the atom looks like experimentally, but how we imagine it is like this, because now I'm also becoming a theory person. So you already imagine an atom in a harmonic oscillator trap, because that's again the favorite system that we love in physics. So it's a three-dimensional trap, but now you can imagine the simplest model to take is there are three harmonic oscillators in each axis. And then in each axis, you can imagine the trap potential to look at near the center. You can imagine the trap potential to look like this, which is a harmonic oscillator trap. And now, by what do I mean by cooling the atom now? The cooling the atom basically now means that there are discrete motional states that the atom can take, and making the atom go down the motional ladder to the motional ground state is what the aim is, to cool the single atom down. So that's what we aim to do, and the cooling beams are we apply cooling beams in all different axes to do the trick of making to get the atom down the motional ladder. And so that's for cooling. When we say we want to cool the atom down, there are three different harmonic oscillators which we want to reach the motional ground state of, and that's our aim with the experiment. So that's what we wanted to do, and that's what we want to do with this beam. So I just wanted to emphasize with this slide that cooling basically implies putting the atom in the motional ground state and not like making the atom stationary, because that's how people imagine laser cooling initially when they get to know it. So, okay, now we are at, yes. Oh, yes, I'm going to explain that. So we have a spatial light modulator, and I have a slide for that. So I will come to that. So now that we have understood, we want to go to the motional ground state. Now we are at a point where I can explain why do we need an arrow line. So now imagine that in each atomic ground and excited state, you have to imagine it as a harmonic oscillator of motional states. So each ground state and electronic state, so each atomic state actually is associated with a motional level. So if we have an atom that is trapped, now going from ground state to excited states looks something like this in the theoretical model, where you have motional states for the ground state and you have motional states for the excited state. So you have to also think about which motional state you're going to if you're starting with a specific ground motional state. So now imagine that you are sitting as an atom, you are sitting in the nth motional level of the ground state. So now this is one of the methods that is used in the tweezers to cool the atom down to the ground state, which is what we are after with this line. It's called a single photon sideband cooling, because what we do here is this ground state has a trapping frequency. So the distance between the levels is actually the trapping frequency of the ground state. So now what we want to do is we want to drive n to n-1 transition, where we tune our lasers with this much detuning so that we drive n to n-1. And then while coming back, it actually returns back down to the n-1 state, because in spontaneous emission, the atom gets a recoil energy. That recoil energy, if you're in a regime where the recoil energy is not sufficient enough so that it gets the extra energy to switch the motional levels, then while coming back, you can be sure that if the atom starts in n-1 level, then it will come back down to the n-1 level. That's called as something called as Lamb-Leakey regime. And in that regime, you can be sure that if you're starting in a motional state, in the excited state, you'll come back down to the same motional state in the ground state. So if we follow these two rules, then we can selectively drive from n to n-1 using our laser. And then while coming back, it will come back to the n-1 level. If we continue this, then you can see there is a net cooling of +1 or -1. And then if you continue this, it will go down the motion ladder to the ground state, which you can see on this animation on the right, on the left, where you initially start with n+1 level, and in each case you're dropping down by one motional level, and then eventually you'll reach the motional ground state. But in this case, if you have noticed on the right, there are two laser profiles that I have depicted. This is a laser profile which is similar to alkali atoms, let's say 5 megahertz line. So it's much broader compared to the one on the right, which is hundreds of kilohertz. Okay. So this is much narrower, which is something similar to the quadrupole line that we have, which is hundreds of kilohertz. Compared to that, we originally were using 5 megahertz line. So you can imagine the trapping frequency generally for neutral atoms is hundreds of kilohertz. That just depends on your trapping laser, and that's roughly the same in all cases, for all different atoms. So hundreds of kilohertz is your trapping frequency. So the distance between the levels is hundreds of kilohertz. Now, if you use a 5 megahertz transition, you are not going to be able to resolve the lines to drive selectively n to n-1. But you need the ability to drive selectively n to n-1. That's why you need a very narrow line, so that will be resolved in the motional states. And that's the reason why we are after this narrow line, and we can do cooling with this single photon sideband cooling technique whenever we want to do cooling in the system. So this is the motivation why we are switching from already imaging and cooling beam of D2 line to a quadrupole line. So yeah, narrow line helps resolve the motional states, and that's why we are after the narrow line. So, okay, so, but this is not the only technique that is used in the tweezers. There are a number of other techniques that are used, and you would be surprised. There is very little amount of literature on this, where you still imagine free space models. So for free space atom cooling, there are a lot of models available to describe what exactly is happening and what are the new techniques that you can use in the for free space cooling. But people still use those models to extrapolate what the mechanisms would be in the tweezer or in a trap system, and that's not very useful because it's a different picture. So what we encountered, like we have lithium in the we have lithium trapped atom in the lab, and we have cesium trapped atom in the lab. So for lithium, we actually used a different technique, and the formalism for it was not available theoretically at all for a trapped system. So that's why we invested some time in theoretically modeling it. And this is a paper that we published literally last week. It was out in the PRA. So this paper was mainly about describing all different mechanisms in the tweezer, and some of which, for example, gray molasses cooling, it's pretty. It was a surprise to us as well when we did simulations and when we modeled it, that gray molasses cooling is actually able to theoretically make it help us go down to the motional ground state, which is still now people only imagine Raman sideband cooling to be the one technique that is able to take you down to the motional ground state. But gray molasses actually also is able to get you down. So in this paper, we have actually listed all different formalisms that you can use for trapped atom systems to cool it down. And they all can be explained actually under the same theoretical framework. So if you read this paper, it's a giant paper, but then if you have time to read it, it will give you models, and it will give you simulations as well, the results, to compare different cooling techniques and decide for yourself which one you want to use for the system. Because depending on which species you choose in the tweezer or in the trapped atom, and also whatever lasers you have available, you can choose different cooling techniques. Because, for example, you can go between the hyperfine states. There are 2-photon cooling techniques, single photon cooling techniques, and we also compare the efficiencies of different cooling techniques. So this is a nice overview of the entire field, and also it has some new results which will hopefully be useful for the community. So this is the paper that we worked on. Just because the motivation started as we didn't have any paper explaining what was happening with gray molasses in the tweezer. So we formulated it, and it turns out that we found many new things. So you can read about it in this paper. So coming back to this cooling technique, which is single photon sideband cooling. So now we have a transition which is narrow line, and we want to use it as a cooling beam. So again, we are going back to this transition, but now we are looking at the specific details of it, which is the line width. Once you send the atom to the 5D state, then it comes back down through 6p3 half. So actually, the lifetime, the line width is determined by this line width over here and not this line width, because that's generally the confusion people get, that why is it not 3.5 hertz narrow? Because once you send it in the excited state, it predominantly decays via that line. And that's why 124 kilohertz is actually the line width of this transition if we drive it. The second interesting thing in this transition is, of course, it's a quadrupole transition. So you can notice this is 4 watts per centimeter square. So maybe at least the experimentalist will know that this is an absurd number, and you won't get it without focusing the light down. So we have to focus even the cooling laser light down at the atom, so that we match the saturation intensity, and then we drive the transition effectively. So that's why we have a line width of 124 kilohertz. We have ISAT of 4 watts per centimeter square. And this is, of course, a quadrupole transition that I have already emphasized on. So now if we have all this, then if we want to do an experiment with it, we just need to figure out how we shape the beam and how we focus the beam, and exactly put it at the atoms and see if we drive all transitions or not. So just to clarify, we want to go from F4 level to F6 level. And then while coming back down, it will come back down from F5 to 4, because while coming back down, it will come back as a dipole transition. So +1 in each transition, and going up is a quadrupole transition. So if we want to use this line, then we first need to 685 nanometers is something that you can get out of a diode laser. So we can get the lasing out, but now we want to make first the narrow line width. So for making the line width narrow, we first lock it down using a cavity. So this is a ultra-low expansion glass cavity that we have with a finish of 10,000. And this is temperature and vacuum stabilized. So we put it in a vacuum chamber and then we stabilize it such that it stays, it doesn't drift at all. So using this cavity, when we pass light through this cavity, we actually lock to this cavity. So the locking is something when you, it's a standard locking again in atomic systems, I guess. So you lock to a cavity using something called as Pound-River-Hall technique, where you pass your laser through the cavity and then you get the reflected light back. Using the reflected light of the cavity, you couple to the cavity and get the reflected light back. The reflected light can be used as an error signal. Once you can generate an error signal through it, and once you have an error signal, you lock to that using electronics. So then this error signal goes to electronics, and then something called as peak locking can be done using any servo amplifier that you have. So that's how you can read this. This is for the details, or you can ask me later as well. But this is a standard locking to a cavity technique, which is Pound-River-Hall technique, and this is the technique using which we define the line width of our transition. So the line width is of this lock is lower than hundreds of kilohertz. So we are anyway going to be lifetime limited by 124 kilohertz. So we don't need a very narrow cavity which will give us, like, there are cavities which will give you millihertz line width. We are not after that because our transition itself is limited by 124 kilohertz. So you don't want to go below that. This cavity or this lock helps us make the laser line width narrow. So now in our story till now, we have a laser of 685 nanometers and we have a narrow line width now. Now the next thing that we want is we want beam shaping. So how do we then, if we want to transfer two angular momenta to the atom, then we not just need polarization of the beam, but we also need the shape of the beam to be precise so that we transfer angular momentum. So to get the second part, which is the orbital angular momentum part, we need some device that will give us intensity modulation of the beam around the atom. So for that, we use a device called as spatial light modulator. Spatial light modulator is a device where you can do phase modulation. You can imprint a phase on the Gaussian laser. So generally, people use Gaussian lasers when they work with this system. So if you imagine now a beam coming in, and then you imprint some phase on it, and then it propagates ahead, then the phase is printed on this. So electric fields, you have amplitude and you have a phase with the electric field. So this is how, using a spatial light modulator, you can imprint a phase on it. And now imagine that we are doing focusing with this light. So once you focus the light down, then at the focus compared to the collimated side, you will get a Fourier transform. So what you're going to get is, if you are doing phase modulation with the beam and then you're focusing it down, at the focus, if you see, you'll get intensity modulation. And that's why, depending on which phase you keep, you can generate like Laguerre Gaussian beams or vortex plus minus beams, which will have angular momentum of -1, +1, or +2, and not just 0. So 0 is like the Gaussian one, which doesn't have any angular momentum. But using a device called spatial light modulator, then you can change the phase of the beam, and then if you focus it down, you'll get intensity modulation. So that's how we generate different orders and different angular momentum of the beam. And that's how we change orbital angular momentum part of the beam, because polarization is like every day, everyone knows how to change polarization with wave plates, but this is kind of the new thing that we have in the experiment right now. So now we are ready with all the experimental apparatus that we have in the lab. So this is how it looks all together. So on your left, you can see there is a trapping laser. So 1064 nanometers, that's the path for that trapping laser. So that is the laser that is focused down to a narrow spot, and that is the one that is trapping a single atom. So now on your right is the cooling laser path, which is the 685 nanometer beam, which is the quadrupole transition. So then the 685 nanometer beam comes in and passes, of course, through a SLM. And this is the spatial light modulator device that we use to generate orbital angular momentum. And then we focus that light down as well at the glass cell. So this is a single atom that you can see at the center of glass cell. And once you image using this line, then if you remember, there is an 852 nanometer photon coming out. So that photon is actually coming from the atom. So we are not providing it at all in the system. But then the photon that is coming out, we image it on the EMCCD single atom imaging camera. And that's how we have 3 different wavelengths. One is 1064 nanometer, which is the trapping laser. Second is the cooling laser, which is 685 nanometer beam. And third is the wavelength that we collect from the atoms, and we don't provide it. So this is how our experiment looks like, and we can generate all 3 different vortex +1, -1, and Gaussian to selectively drive +1 angular momentum transition or -1 to change the orbital angular momentum and then drive selective transitions. So this is how our entire setup looks like in the lab right now. And right now, I've only talked about actually cooling lasers and not talked a lot about trapping laser, but it will play a part in the story. So if you see next, now we have all this system. So can we, now let me demonstrate the results. Can we actually drive these transitions that I'm promising you in this line? So with selection rules. So again, I want to emphasize that yes. Like the focus of this beam. So this is like tenths of micron. Yes, so on the atom plane. So I think our tweezer is like a micron. So about both sides around it is like tenths of microns is our beam size, right? So because the actual size at the atom is like 6 micron for this beam, but then we can choose to like that's the Gaussian size. So Gaussian size is like 6 microns at the atom. And tweezer is 1 micron. So the waist of the tweezer is 1 micron. So now we can generate, and we can change the inner radius actually to change the size, like size of the dark center. We can change the size depending on what we keep. How do you image this? So the imaging light, yeah, I'll actually come to that. So that it's something that is also something new. So I mean, the light that is scattered. How do you? Sorry, wait. Is the question how do you image the cooling laser?
Yeah, how do you image this beam profile?
Oh, so that beam profile is directly from the same beam path. So actually, what comes in is 685 and 852 at the EMCCD camera, right? So if you just remove the filter and then there is no atom, then you can also see this beam on the EMCCD camera. So if we want to image the single atom, which is like the photons coming out of the atom, then we put a filter so that we block this light. But if we don't want, if we first want to see that the light is there and at the correct position or not, that we can do using just removing the filter. Okay, so this is the system that we have. And can we drive the transitions that we promised? Yes, we can. So now you have basically a system where you have different knobs. So you have orbital angular momentum that you can change from +1, 0 to -1. And then you have polarization, which is sigma plus, sigma minus, and 0. So you can choose any of these to go from the four state to like 6 manifold. So these are all MF levels, and this is also MF level, and this is F level. So if you want to change from, let's say, if you want to go do a transition from ground state to excited state with +2 angular momentum, then you can choose +2 is literally vortex +1 and sigma +1. So all different combinations can give you all different transitions from -2 to +2, +1, and +-1 and 0. So these are all transitions that we can drive in the atom manifold. And to show you the signal on the atom. So if we just change, because the spin part is actually the usual part. So people always use selection rules with the spin part. The part that is interesting is changing the orbital angular momentum, because that is even the selection rules, driving different selection rules for beam shape is not shown till now in atoms, in neutral atoms. So that is something we show. So if you put vortex -1, then you drive one selective transition with 4,4 to 4,2. Then if you put Gaussian laser, then you only drive 4,4 to 4,3. And then if you want to drive 4 to 4, then there is, so the polarization is kept constant here, which is sigma minus. So sigma minus and vortex plus gives you 0 transition. That's why there is a pi transition going on here. Sigma minus and 0 orbital angular momentum gives you -1 transition. And sigma minus plus -1 orbital angular momentum gives you 4 to 2 transition. So you will now see actually there are peaks at the center for all these 3, and the only peaks along the side are changing. But the reason for that is our donut is actually not perfectly, the intensity of the light is not perfectly 0 at the center of the donut. That's why the central maximum transition that is driven due to the polarization is always driven, because there is some intensity still at the center. To get the best intensity, like get the dark center perfectly dark, we actually need another SLM. And there is a reason for not we cannot use just one SLM and get perfectly dark centers. That's a limitation we have to live with. But this is just demonstrating that if we change orbital angular momentum of the beam that we are keeping at the atom, we are able to drive different transitions selectively. And if you want to see all of them together, then this is the selection rules. This is basically shaping the beam and then driving different transitions for the selection rules. So now, yeah. Yes, that is due to aberration.
Yeah, so
That should not be there. Yes. So actually, I mean, this is not the case with this transition, but sometimes we see that the strength of this key is also dependent on how much transition, because like I said, quadrupole is also with it also depends on what is your gradient. So now you can imagine if the intensity is not great at the around the edges compared to the center, then the gradient is also small. So that if the gradient is small, then you will get less intense transition. So that's why in some of these cases, even though it's not true here, that's not necessarily the only reason why. But we do get asymmetries by looking at just the beam shapes and how the beam looks at the atom between vortex plus and vortex minus. If the beams don't look perfect, if they are not identical, then we do see that.
So why does vortex plus and minus have different operations? Like different.
I don't know. I don't know. If I could fix aberrations, I would, but yeah, that's something that we get. Actually, it kind of depends on what. I mean, SLM's active aperture is also like a finite amount. So sometimes we have seen that where we keep the beam on the SLM, it slightly changes how perfect the pattern looks like. It is not exactly like it should not happen in theory, but this is something that experimentally we need to figure out to like correct for the aberration. So I don't know why they are asymmetric. They should not be asymmetric, but currently this is like. But I think we can work with aberrations and then we can reduce it further down to make them exactly symmetric. Then this effect should go away.
Yeah. How your aberration work with phase modulation is you like phase offset onto that. So if you have same offset for +1 versus -1, you have it like over tuned for +1, so it's like 1 point something, but you are under tuned for negative 0 points. So that's why it's symmetric, like minus 0 points versus +1 point. Yeah. Overtuning in phase, like the phase is not 2π, but like 2π plus something. And yeah.
I guess he's.
Like phase.
Yeah. Of course, you can use AI to help.
Yeah, this is kind of the phase pattern that is. Okay. So yeah, we can drive transitions and so this was only demonstrating selection rules for beam shape. If we add polarization to it, then we can drive the entire manifold starting from 4 and -4 to all different transitions. And then this is a different detection, like this is a different experiment altogether. But the main thing that I want to emphasize here, if you combine the selection rules for spin and polarization, so spin and beam shape, then you can drive selectively all different transitions in both cases. So this is like free space resonance, which is going from 0 to 0. And then if you add the two, then you can drive to the right. And if you add to the left, you can drive to the left. So we are able to do all selection rules that are possible in the system because of having two angular momenta. So with this, we are able to drive all the transitions. So how can we do cooling now with this? One last ingredient for cooling is still trapping laser. So trapping laser will come into picture now. We have this transition. Remember, it's an arrow line, so we should be able to cool with it. Now, I talked about this picture where you have a harmonic oscillator and then there are discrete motion levels, and you want to go to 5D state and come back. The part that I omitted is this is an ideal picture. This is not something that you get in this is not something usually you get in neutral atoms. These two potentials look very different in neutral atoms, and you have to work to make them look exactly the same and then implement this cooling method. So that's the remaining step that we want. So the shape of the potential depends on the polarizability of the atom in that level. So if your excited state 5d 5/2, imagine that has a different polarizability compared to 6s 1/2. Then the shape is going to look very different, and even the spacing is going to change in the excited state compared to the ground state. So now what is the realistic picture is, this is an idealistic picture where you see the potential is exactly same excited ground state, but the realistic picture looks something like this. You can get the excited state as more trapped. So if the polarizability is more in the excited state, then it's more squeezed down, and then your spacing also changes with respect to that. If your excited state is less trapped, then you get a narrower potential, a shallower potential, and then your states are closer to each other. So now, because of this, you can imagine an effect. You don't get a magic condition readily available in the atoms. You do get that in ions, so that's why that's an advantage for ions. But we can tune this. So the way we can tune this is, there are two knobs for it. So this is happening because of the trapping laser, that is an external potential at the atom. So the trapping laser has two components. One, it's the wavelength of the trapping laser, and second is the polarization. So we can change the trapping laser's wavelength to make this transition magic, or we can change the polarization. Now we have a really good 1064 nanometer laser in the lab, so we don't want to change the wavelength of the transition. But we can tune the polarization. The effect that you see, if you keep your system like this, the reason why you can't cool is because, now imagine that you're continuously cycling from ground state to excited state, and it's coming back. So now if it's doing this cycling continuously and you want it to cool down, then what the atom experiences is a fluctuating force, or fluctuating dipole potential as it is going up and down in the excited and ground state. So what that does is, this changing potential acts as a force on it, and then that heats the atom out. So of course you don't want heating to go on continuously as you're trying to cool down the atom actually. So you don't want any of these two scenarios. You want to go magic, and where the potential in the ground and excited state look exactly the same, and then implement the cooling that I talked about earlier. So to do this, we have to find a magic polarization. So are we able to do that? Yes. So what we did is, we changed the polarization of the tweezer with a coordinate plate, and we found a magic polarization, which is where even our calculation suggested that we should get a magic polarization at a specific ellipticity. So we change the polarization of the tweezer, and then we see the light shift at the atom. So the idea is, if you are at the magic condition, which is this condition on your left, then your frequency of transition from this to this should not change at all if you're changing the tweezer power. Because if you're changing the tweezer power, both the potentials should look identical irrespective of what your tweezer power is. But if those two are not identical, then they will separate, and the frequency of transition will change if you go from this to this. So now what we are seeing here is, the zero crossing point, where you get zero light shifts, is the magic polarization, where you can, looking at this graph, you can say that the zero crossing point is the polarization at which your ground and excited states are magic. And that's the ideal case if you want to do cooling at all with the atoms. So this is the case that people generally choose, either using wavelength or polarization of the light. So once we have this, what's the proof that it's magic? So we do measure transitions, and these are all different MF level transitions. So if you look at the stretch state, which is 4 to 6 transition, then that's the rightmost stage with highest frequency. Now, if you look at different tweezer powers, if you measure the same transition at different tweezer powers, sitting at the magic angle, then you'll see that the transition that you're looking at, this 4 to 6, is not changing at all in frequency. So it is almost at the same position. So it is very close to magic. And that's what tells us that the polarization that we are at with the tweezer is actually magic. And then we should be able to do cooling with it. So this was the last piece of puzzle that we needed for cooling. And with this, yes. Yes.
A quick question. Do you worry about, so you can achieve it empirically, the magic, but because the high-T focus beam also develop actual field, things like that, and do you have full understanding on how the polarization will look like when you can achieve magic?
Wait, is the question that since it is focused down, the polarization should change depending on where the atom is with respect to the tweezer?
Yes.
Yes. We will see an effect of that, but if it's very hot, we should see that effect. I think if it's very cold and it's very near to the center, and polarization of the tweezer, if you are very close to the center, it should not change a lot. At the edges of the tweezer, yes, if your atom is very hot, then if you're at the edges, then it is slightly circular, like it has slightly different polarization compared to the polarization that you want or ideally is sending in. But we did measure, we did actually do a polarization measurement at the position of the atom where we are keeping it, and then we saw that it is actually the polarization that we want in the system. So later we did not worry about it, and we actually see as well with this graph that whatever polarization we are keeping, we are getting similar polarization at the atom. So unless your trap is very wide and you're sitting at the edge of the trap, you should not see a lot of many effects with that. Till now, we haven't seen at least. Okay. So we have the magic polarization. Now, do we cool? Yes. So what's the test of cooling for a single atom? Because for multiple atoms, you take average kinetic energy, and that's your temperature, right? So that's how you define a temperature, and then you say the atoms are cold or not. So you let the atoms go, and then you see how fast they're going away. And if they're cold, they'll expand slowly. So that's your definition of temperature. But once you are in the tweezer, then you have a single atom. So then you can't have multiple atoms. So with a single atom, then what's the definition of temperature? So now it's the distribution of the states, distribution of motional states for a single atom that defines how your temperature is. So what this experiment is kind of similar to the time of flight experiment that people do with multiple atoms. Is you have a trapped atom, and then you for a few microseconds actually you turn off this trap. And when you turn off this trap and turn it on after a few microseconds, do you capture the single atom back or not? That defines whether your atom is cold or not, because then that distribution is what we fit to Maxwell-Boltzmann distribution, which is classical distribution for a temperature, classical temperature definition. So what we are doing here, theoretical picture is we have a deep tweezer, and then we are shallowing it down and bringing it back again. And what is the probability that we don't lose the atom? So that probability curve is actually what gives us the temperature. And then we can fit this temperature and also get average motional state where we are in the tweezer, because that is the number that is important to us and not necessarily the temperature. So the temperature, we do see initial cooling results with 5D beam when you interact with it. Before interacting, it has a 50 microkelvin temperature, but after interacting, we are able to cool it down to tens of microkelvin, which corresponds to average motional state of 4. So we, in radial case, so there is an asymmetry in tweezers as well. So there are 3 different harmonic oscillators you have to think about. But in radial case, we have reached n equal to 4 in the ground state. So we are at n equal to 4. Our target is to go to n equal to 0, so the lowest state. So we are almost there, but not yet to the ground state. So this is the cooling result that we have till now. Another exciting thing that I haven't mentioned yet is background free imaging. So you get this kind of as a bonus with this line is you get background free imaging. Now, how imaging generally works with alkali atoms is you image on a D2 line where you go from F4 to F5, and then the spontaneously emitted photon is what you collect on the screen, on the single atom camera. So this is how the histogram gets built up for us. This is a single atom dipole transition histogram where we do the experiment every time and we take a single shot image. So in that image, how many photons are collected at the spot where we think the atom should be? These are the number of photons, and how many times, let's say 80 photons are collected in the experiment. If we repeat the experiment for 1,000 times, then this is the occurrences for the number of photons that you collect. So this is how the histogram gets built, and this is how we can, so if there is no atom, for example, then there will be very few number of photons that are scattered, but there will still be some photons because you are imaging with the 852 nanometer beam. And that's why even if there is no atoms, there will still be scattering around the chamber that will be collected in the camera. So that's why your no atom peak is always going to be there. So there will be some background of 850 nanometer light always in the imaging picture. This is how usually imaging works with cesium. But now, and this is how after the histograms get built, this is how the histograms look like. And out of those, this is a single atom peak, and this is a no atom peak. So actually, no atom peak, how do we decide or how do we determine whether the single atom is captured or not? We image this and then we count the number of photons that are there in the pixel area. And we then put a threshold saying that first take an image which is background image. There is no single atom there. So the highest number of photons that are collected, let's say it's 20. So we put a threshold here at 4, saying that if we collect any more photons than this, then we have a single atom. So that's how we distinguish between single atom peak and no atom peak for a single atom histogram. So this is an image that you can see on your left, is a regular image that you do with imaging. So till now, cesium has been imaged with this line for all the experiments that are done with cesium. But if you instead use the line that we are using, which is a quadrupole line, how does that improve the histogram at all? So remember that this is a background peak. So this ideally should go away if you don't have any background. So with 5D beam, the advantage is you're sending in 685 nanometer beam, which you can filter out at the camera before putting a filter on the camera. So filter out the 685 beam. So the excitation laser is completely filtered out from your image. So the only light, which is 852 light, that is coming is from the atom. So any photons that you collect on the camera is going to be with the atom, and that is going to be your signal. So your signal to noise ratio is amazing if you already have a filter which is completely going to block out the light that you're exciting with. And do we see this in the experiment? Yes, we do see that. So you can see the difference between these two images, and you can see the background is completely zero now because we are able to collect. So the background is literally zero. But the reason why the histograms are not separated is because we are not exactly in the cycling transition case, because once it goes to F6, it is depumping down to different MF levels, and that's why we don't have the separation with the histograms. But once we fix that, this is going to give you a much higher fidelity or much higher signal to noise ratio compared to the usual imaging case. And that's why people can switch from imaging using the usual line to this line, because this essentially gives you background-free imaging. So there is literally no background other than, so any photon that you collect on the camera is going to be a signal. So that's pretty.
What is your imaging time?
Oh, for this image, it was 30 milliseconds for this image. So right now, we can reduce it further as well. But the reason is we are not, like I said, the histograms are not separated right now. So we are not able to generate a lot of photons compared to what we generate in the usual case. But once we are able to separate them, then I'm confident that we will be able to lower the imaging time to even a millisecond, and we should be fine. So that will also help in imaging quicker, which is kind of useful for experiments later when we want to do application. So that's background-free imaging. And so to summarize, we are trialing a quadrupole transition in atoms, which is again for the first time in tweezers or any trap atom system. We are getting background-free imaging, which is another first-time thing that people have never done. And this is still the preliminary cooling result, but ultimately what we want is with this line to reach motional ground state. Right now, I think the limiting factor for us is we are not cooling in all 3 axes because we are focusing the light down, the cooling light down. That's why the focus is actually just 2-dimensional trap. And then it is able to effectively cool in 2 dimensions, which is the radial dimensions, but it is not effectively cooling in axial case at all. And that's why we are now thinking that if we go off axis, then we project on all 3 degrees of freedom of the tweezer, and then we will be able to cool in all 3 axes, which will give us much better chance of getting ground state cooling, for example. So that's where we are at with the experiment right now. And that's the summary of the results. I would like to thank sorry for the new students. There are no pictures for new students yet. I didn't get the pictures from them at meantime. But yeah, do check out this paper as well. Thank you. Rest are appendix slides, so don't
Have you tried measuring the lifetime of the 5D signal?
Yes. I mean no, actually we have not done. So whenever we measure, the narrowest transition that we can measure is 124 kilohertz. So we have measured the width of that transition, but we have not. So we have spent a lot of time in doing spectroscopy, understanding the light shift, but we have not. I guess if that line is narrow enough, then we can say that that's the limiting line, right? So
for precision measurements, though, the product of the line width and the lifetime aren't exactly 1 or 2 pi where it's supposed to be.
So that
we could replace the interval with an APG.
Oh yeah. we haven't done that yet. Yes, yeah.
There are a couple of different measurements in the last 20 years, which don't agree.
Oh,
And I can't see any essential difference between the measurements. So it's nice to, the most recent one agrees with the theoretical calculations for the matrix elements from the 5D to the 6B.
oh,
But the earlier ones don't. And I don't know what the difference in the measurements was.
because we are actually in the lab, we are doing right now a lot of experiments with understanding the like vector scalar shift or tensor shift with the tweezer. And that is requiring us to compare with like the matrix elements from a theory group, Safranova.
Yeah.
So yeah, so we are finding some disagreements there, but we first want to be like really confident that these are the lines. And then once we are confident, then I think that is also another measurement using which we can compare with the theory. But yeah, maybe in future we can investigate. Work with people, we can, yeah.
I don't know how important it's up to.
I have a question. Hello?
Yeah.
Yeah. So you previously mentioned that you haven't reached a cycling transition yet, but what's limiting you from reaching cycling transition?
So we are right now, what we are keeping is an optical pumping beam to pump to 4-4 state. Earlier, what was happening, and this is our current model that why we were not getting cycling transition was if we go to 4-4 state, actually let me pull back the slide to exactly tell what I wanted to. Yeah, so on this manifold, if you are starting in 4-4 state and if you're going to 6-6, what's happening is after a few scattering events or after, actually not few, so many scattering events though, but after many scattering events, we are going to different MF, not different F, but we are going to different MF. And then I think that is limiting the amount of photons that we scatter on average when we take a single image for like 30 milliseconds. So for example, when we are imaging for 30 milliseconds and let's say for 1 millisecond only it scatters and then goes to any other MF, we are not on resonant to other MFs. So that's why we are not able to image on the, if it goes to any other MF in F4 manifold, then we are not able to image there. And that's why that is kind of, the MF depumping is actually kind of the limiting factor. So how we are going to improve is actually just keep an optical pumping beam in between doing imaging cycles so that if it depumps in the F4 state, then we are able to optically pump back to F4 and then that will keep it cycling. So it's kind of a similar idea that people use in mods, but in magnet optical traps or for normal imaging, you use F depumping line. The repumper line is for F repumper. So here, our main problem currently is, I think, MF depumping and not F depumping.
Okay, I want to make sure. So it's because of all resonance scattering driving to other F prime states, and therefore you pump out the stretch state.
Yeah.
Okay. I have one more comment.
Yeah.
You said that this is the first background free imaging. It's actually people did 2 photon transitions and then background free imaging. So in terms of background free imaging, this is not a first.
Okay.
This is the first using this transition for background free.
Sorry about that.
Yeah.
So what do you say that No, we are sure. So it's fundamental with the tweezer that you have axial trapping as weaker compared to radial trap because because of the symmetry of the trap, it's in 2D. So then you won't get because it's gradient of the intensity that is actually helping you to trap. So actually we do trap, but then the trapping frequency is much smaller. So now you can imagine with this picture that the difference in motional levels is going to be proportional to the trapping frequency. If your trapping frequency is high, then you're going to motionally be resolved. If your trapping frequency is low, then they are going to be close together levels. And now you can imagine with 100 kilohertz line width, if we have 20 kilohertz spacing, then that's not going to be great cooling results for us. That's why actually it's going to be difficult to cool compared to radial. Yeah. Yes.
Sorry. Maybe just like an interpretation thing, like when you talk about like the semi-classical picture, like the thing that's causing the trapping is like the gradient of the electric. And then but in this picture, like they're literally absorbing photons. And so like how do you reconcile like not having any intensity at the location of the atom and still being able to absorb?
So the average intensity is not average intensity is zero.
Yeah.
Not like so instantaneously like there can be intensity at the atom. But then if you calculate like the average of all the intensity, then they effectively cancel each other out. But then at a moment, and that's my current understanding, that for a sec it can see an intensity, but then if you average it over time, mostly it's going to be zero at the center. So
I mean, it's called the saturation.
yeah. Oh, so it's not necessary that we always need to keep it at the dark spot to drive that transition, because you can also drive it with the gradient of the electric field. So gradient of the electric field is actually needs to be non-zero, but it's not necessary that it will only get that when the intensity is zero. You can also get that by like there are multiple calculations for it. But yeah, so if you go to spherical coordinates, or if you transform, then different gradients in different axes can give you even so we are able to drive this transition even using Gaussian beam. It's not that we are able to only drive it using quadrupole beam, but we have to project the correct vector on it so that the gradient will still be non-zero. So at the edge of the Gaussian beam, you can imagine a gradient being non-zero, and then you can drive using Gaussian as well. It's just that it will be driven more effectively because of the steeper gradient in vortex. But there are other ways to drive it even when intensity is not zero.
And then maybe
Could you show the slides where you compare MF equals different angular momentum beams and driving different transitions? Yeah. Can you one more slide? So one thing I'm curious is that so if you have a perfect, if you just have a Gaussian beam, it seems like there's no way you can drive other transitions. But somehow if you have vortex -1 or +1, you can drive both one more change of angular momentum or just or 4-4 to 4-3.
So the reason why, because in this case we picked the atom's position at the center of the Gaussian, and we also catered the polarization such that it only drives this transition, which is a -1 transition. But we have scans where we see multiple peaks. For example, like all these peaks all these transitions are 4 to 6. We are able to drive this entire manifold with just Gaussian light as well. The trick is you do have to change like the position of the atom with respect to the Gaussian. And in Gaussian, there are like the radial gradient acts differently than axial gradient, and we also know it's the focused laser. So
okay, good. That's exactly my question. So if you make the Gaussian beam slightly off from the atom position, you can still try all those transitions.
Yes.
Okay, good. Thank you.
I guess, yeah.
Yeah, so like just like maybe like so like the more common technique is like Raman like typing cooling. So like what are the benefits to doing this over?
So this requires just one beam which is focused down, right? Raman sideband cooling, if you're familiar with the technique, it requires like 3 different focal beams which are centered at the atom, and then you have to align the k vectors of the beams to exactly like transfer specific k in each axis, because you need 3 beams because you have 3 harmonic oscillators. Yeah. So then you have, if you want to project exactly the k vector that is needed in a specific direction, you have to align it and make it such that till you get to the ground state, you need that alignment in all 3 axes. The problem is not even just that, because once you align it and then you go to molecules, let's say with ground state atoms, and you go to molecules, then you have to maintain that for a long time. So to get that, if your beams are misaligned slightly, you lose the amount of cooling that you're getting. So the alignment procedure is actually what is a more difficult thing than theory is well understood for Raman segment cooling. So it's not theoretically it's not a problem, but experimentally speaking, I think John faced this issue mainly. It's his motivation to find like a different transition for that, because in the last lab he also observed that keeping it aligned is like kind of it's not difficult. People are using it a lot, but
Is there like something in your experiment where you would think to yourself, if you're going to start a new experiment, you can change it?
Well,
This
it's the process of studying it.
is the thing. The problem, if you're doing one species, I think Raman segment cooling is fine. Okay. But when we're doing molecule creation, the efficiency at which we can make molecules is determined by the ground state population. So you really need to do ground state for both species. And one is fairly hard. Doing two, that's a lot of beams going into your system. They're focused down. It's like 6 beams.
Cooling beam.
And then also it's extremely sensitive, usually very off resonant for those beams. You end up being sensitive to like milligauss fields. So it's just, I spent probably a third of my time optimizing Raman sideband cooling. And so my feeling was that if this was going to be a experiment where we can really progress with the molecules, we need to get the atoms in a ground state in a much more robust way where we're not always doing it.
actually there's we have this idea, the cool idea that we also said in the theory paper, that if you add a beam to your, so we have gray molasses cooling that is works with just normal lasers which are not focused at all. So there is a idea that if you add a optical pumping beam in a different direction, then that Hamiltonian will look very similar to Raman sideband cooling Hamiltonian. And then you can read about it in the paper, but it's just an idea which will simplify the cooling a lot, which is using a different technique, not the single photon one that I mentioned here. But if that works, that would also be potentially useful for as an alternative to Raman sideband cooling, for example. But that's not something we have tried. So this theoretically it should be okay. That's. Oh, so you have one focused beam, right? And then if you right now, I said our issue is right now we have only good cooling in radial direction. But now if you have a focused beam, imagine that with focused beam, why do you even Raman sideband cooling require focused beam, right? So with focused beam, you get all different kinds of K vectors. So now if there is a symmetry with tweezers that you want to project, the key is to just project your light so that it projects in all 3 axes of the trapping. So you have 3 harmonic oscillators. You want to project on all 3 harmonic oscillators at the same time. So now you can imagine if you go off axis with your tweezer, because I'm constantly saying this because if your collimated beam is going in and then you are focusing down using a lens, imagine that this focusing down through the center will only project on the radial cases, on the radial axis, because of the symmetry. Yeah. But now imagine that you are going off axis and then you're projecting from one side slightly, then that should project some on the axial case as well, because it's now not parallel to the axial case. Yeah. So if that happens, then we should be able to project some of the K vectors on the axial trapping as well, and that should give us enough. Axial one?
Like the axial and the radial one are different.
Yes, trapping frequency. Yes.
Yeah. So then you can't use one meter.
No, I mean once we are very cold in a radial case, actually it's also a merit or a demerit that you get all 3 axes as decoupled. So,
but I'm saying like you need to do you only have one.
Yes.
You want to.
But this will project on all 3, right? This will not
project on all 3.
Yes, but the frequency will be different.
Yeah.
So frequency will be different to tune for radial case versus axial case, right? But what I'm saying is if we keep a frequency and then we cool down radially first, it should remain cold, and then we can focus on the axial one and then bring it cold.
So you can change the frequency.
Yeah, we can. Yes.
Are you able to drive the Rabi oscillation
between these states? Yeah, I mean we have not observed, we have not made like a measurement specifically seeing the Rabi oscillation. We recently attempted it, But we should be we should be able to see if we are really careful about it. We haven't yet done that experiment, but we should. With that, because W oscillations is how actually even in ions case, this was first demonstrated. The quadrupole transition was first demonstrated. Selection was in ion case. They also did like W oscillations between a ground and excited state. So we should be able to do that. We haven't done that yet.
Question that we can magic using polarization.
Yes.
The magic wavelength.
Magic wavelength is 803. For so no. Oh. No, so we are not using that wavelength. So what we are using is polarization to get magic. But the other way you can do magic is also using different wavelength. So we are not using wavelength to tune the polarization, to tune the magicness. We are using polarization to tune. Yes. Polarization depends on the trapping laser. So yeah, so the cooling laser is actually what we are going to off center. Questions?
If not,